Good morning, good afternoon, everyone. Thank you for joining this webinar on metal replacement in non-automotive applications. My name is Michael Kriek, Marketing Communication Manager at DSM Engineering Materials, and I'll be your moderator for today's webinar. Before we start, please note this is a live webinar, and we're happy to receive your questions. At the end, we'll be hosting a Q&A, so feel free to submit your questions via the questions panel available on the right-hand side of the screen. Or if you're following us via the GoToWebinar app, make sure you click the question mark icon and submit your question there. I'll now give the floor to Jinish. Doshi, please go ahead.
Good afternoon, everyone. My name is Jinish Doshi. I'll start with a quick introduction of myself. So I'm working as an application development engineer at DSM Engineering Materials since 2019. I have studied polymer technology at University of Applied Sciences in Aalen, Germany. I have more than 12 years of experience in application development and technical sales in the engineering plastics field. And I worked in India for a few years, then since last 5 years, I'm based in Germany. We will go through just agenda for today. Looks like this. So we'll start with a short introduction, followed by drivers for metal replacement in some non-automotive markets, what are the solution directions, some material selection criterias, the key properties you need to look at, and then we'll follow it up with some cases in different market segments, and we'll close it with a short summary. If you look, this is a good overview of several applications of market segments where DSM is active in. So you can look at several segments like auto power equipment, power distribution, cookingware, industrial pumps, connectors. So there are a range of applications and segments where we are active besides the automotive market. For today's webinar, I chose to focus on 4 out of these. So I would say consumer goods, water management, industrial, and electrical and electronics are some of the segments which I chose for today's webinar. And across all these 4 segments, cost and weight reduction is a key driver for metal replacement. And if you look at specifically consumer goods, then it could be better aesthetics or design freedom that plastics provide over metal, which can be a major driver, or elimination of secondary operations like coating or painting. In case of water management, some of the key drivers are corrosion resistance offered by plastics. It gives a lead-free solution, ease of handling and installation. And in case of industrial segments, it could be low wear and friction or avoiding secondary operations together with corrosion resistance. And when you look at electrical and electronic segments, thinnovation, which means a lot of mobiles or tablets that we use, they are going thinner by the day, and there is a requirement for structural frames or structural parts which needs to be thin, and there is always a demand for materials that flow well, has a good Weldline strength, and are having good strength and stiffness. And of course, thermally conductive and EMI shielding is together in combination with lower cost and weight. So this is not an exhaustive list of drivers, but these are some of the key drivers which I could list down for each of the segments. Looking at the solution direction, so there are different ways in which metal replacement could be done. So you can go for a multi-material solution, as you can see on the left, where you use an insert and you mold the plastic over that insert. So it's an insert molding or an outsert molding. It could be a metal plastic, a hybrid component, or it could be a 2K molding where you combine a hard and the soft material. So you might use this solution when you want that plastic takes the more of the stresses, and metal take more of the stresses in the part, and the plastic is used more for a functional integration. Another way or another solution is advanced composites. So you see a picture of a liner of a hydrogen tank or a CNG tank, and it's a full plastic liner, and it could be wrapped with unidirectional glass or carbon fiber tapes. And it could be wound completely with the tapes, or these tapes could be also used to place in the plastic part on some local areas where high loads are there in the tool. And so it could be used in different ways. And the third solution is a full plastic solution, which is most efficient in terms of weight and cost reduction. Some of the solutions for complex and challenging applications. So here I would typically like to highlight a couple of applications. So one on the top left, you see our in engine infill panels in case of aircrafts made out of our PA46 30% glass fiber reinforced high flow grade. And these panels can be 40 centimeters long, and can have wall thickness as low as 0.8 millimeter in some of the areas. So this is we could use this material over here because of its very good flow properties, and of course lighter weight which this grade offers, and of course very good impact strength that it offers in the temperature range of -50 to 150 degrees C. And you need to protect the engine against the bird strikes. So that is kind of a very interesting application. Another application which I would like to talk about is an electric control unit cover where a die-cast aluminium was replaced, and with a thermally conductive PA46 Stanil grade in this case. And here there were some other requirements, so we could also achieve functional integration into this part with plastics. And there were also additional functionalities like EMI shielding in the range of 40 to 60 decibels, and thermal conductivity, which was achieved with a plastic solution. So in general, we can say that we could achieve approximately 40% lower weight and 30% lower costs in different metal plastic replacement applications. DSM has a strong track record in metal replacement. So whether you look at consumer good segments or water management or electrical electronic segments, so I just tried to put together some of the pictures of the applications where we could successfully replace metal with plastics. We have a very broad portfolio, an extensive portfolio of semi-crystalline engineering plastics. So right from polyamides, PPAs, PPS, and polyesters. And DSM is a leading innovator in high performance plastic materials. So as far as material selection criteria is concerned, there are different factors which come into play, and some of the key factors which I listed here are the environment, performance, design, and processing. So you could the part you have to look at the environment in which the part is going to be used. What are the performance criteria for the material? The design criteria like functional integration, ribbing, looking at the warpage, wall thickness, and of course processing, where surface quality or gate location could play a role. So I will highlight or touch upon some of the points in the coming slides. Glass transition temperature. So in case of semi-crystalline materials, I just try to show a curve of modulus over a different temperature range for a semi-crystalline material. And the red line that you see, it crosses this curve. The point where it crosses, it's the glass transition temperature. And beyond this temperature, the plastic will use most of its stiffness, and it is very critical when you select the right material. So the polymer enters into a from glassy state into a rubbery state at this temperature. And I put together glass transition temperatures of different polymers that we have, and right at the bottom you see 40 ACE, which is our PPA, which has a TG of glass transition temperature of 160 degrees C. So a pretty interesting material for high temperature mechanics. Yeah, another factor which needs to be considered is because polyamides tend to pick up moisture, and I just try to plot tensile strength of different polymers with 50% glass fiber reinforced here in dry as molded and conditioned state. And as you can see that in the dry as molded and conditioned state, with PPA, there is a very small difference in tensile strength in case of PPS and PET. It is remaining constant because these are the materials which hardly take any moisture. So for high precision parts, it would be PPS or PET, which could be considered. And of course, when you go at higher temperatures, then there is a drop in tensile strength with plastic. So this also has to be considered while looking for metal replacement applications. And you can see that in all the grades, so here I have compared PPA, PPS, and PET glass fiber reinforced grades, and tensile strength at 23 degrees C and 90 degrees C. And in spite of the drop, the strengths are still good. And so 40 ACE, if you are looking for applications where good strength and stiffness at high temperatures are required, then it would be 40 ACE would be a very interesting material to look at. Weldline strength. So weldline strength is basically in case of a plastic part where the two melt flow fronts meet. And this is the area where you would see that the glass fibers are oriented perpendicular to the direction of the flow of the plastic melt. And this could be a point or area in the part which could be the weakest. Yeah. So here I compared the weldline strength of different 50% glass fiber reinforced, and here it is 40% PPS. And you can see that we have a very high weldline strength in case of Stenil, which is a PA46 GF50, and a PPA GF50, which is our 40 ACE MX53T. And so if you have parts with complex geometries or you have weld lines in unfavorable positions, then probably you could also look at these materials. Creep resistance. So this is another key property which needs to be looked at, and I just use one of the application examples here to explain this. So we have a heat shield in a chainsaw here where there were metal compression limiters were used together with a PA66 GF50 grade, and we could eliminate these compression limiters altogether with a solution based on 40 ACE MX53, which is our PPA GF50 grade, and we could achieve cost and weight reduction, significant cost and weight reduction. And the graph here shows that the axial forces would remain useful over the complete lifetime of the product with the 40 ACE, even without metal compression limiters. Hydrolytic stability. So this particular property is more relevant for the applications in the water management sector. So where the plastics are constantly in contact with water for a very long time. And I have two plots here and three different materials which we compared. So the purple one is our PPA, 30% glass fiber reinforced. The red one is PPS glass fiber reinforced, and the green one is our PA410 glass fiber reinforced. And we see when the tensile bars are fully soaked in water at 90 degrees C, after 5,000 hours, we could see that there is a tensile strength retention of almost 80% in case of PPA GF30, and about 70% tensile strength retention in case of our PPS and PA410. Another plot on the right side is to show the oxidative and hydrolytic stability. To check that by aging these tensile bars at 110 degrees C in 100% relative humidity conditions in an autoclave. And here we see that the tensile strength retention for 40 ACE was almost 100% after 5,000 hours. And with Zytron about 80% and Ecopax about 70% after 5,000 hours. So for long-term hydrolytic stability, Zytron PPS and our 40ACE would be the best candidates. I use a couple of case studies from different market segments. And to start with, I have an application in electrical industry, which is LED heat sink. So a lot of aluminium is being used for this type of applications, and we could replace the aluminium heat sink with the thermally conductive PA46, which is our Stanil TC502 grade. And a significant weight reduction, about 50% versus metal, was achieved. And so the plot or the picture on the top right, you see that by using a thermal conductive grade, so this is a non-conductive grade where peak temperatures of 196 degrees were there observed, and then in case of using a thermally conductive grade, we could achieve the maximum peak temperatures by about 26 degrees by dissipating thermal loads. So this is an example from an automotive application, which is a fog lamp, but I just use it to explain this thermal conductivity, how it helps. And another point I would like to make here is applications like this, there are a lot of fins, and these fins have to be also designed in a proper way. So like the distance between the fins, the thickness of the fins, and the number of fins that you provide on the part. And DSM here has a very good knowledge, in-depth knowledge about how to simulate this, so we can help or support the customers in doing the simulations and helping the design of the product with our materials. We have a very broad portfolio of conductive compounds. So based on Stanil, Arnite, which is PET, Zytron, PPS, and Aculon, which is our PA6 and 66 grades. And depending on what you need, so if you are looking for thermal conductivity, then you could use grades with high thermal conductivity. If mechanical properties, performance is important, then you could choose grades which are together with glass fibers or carbon fibers and are also conductive. And then there are grades which are electrically insulating and electrically non-insulating. In water management sectors, also we could replace, in this case, a brass complete faucet mixing valve out of brass with a multi-material solution. In this case, a PA410, 50% glass fiber reinforced. And as per information from our customers, there was no leakage during the complete lifetime cycle test, up to 1 million cycles observed in this part. And of course, superior hydrolysis resistance was another key property of this material, which helped us fulfill the requirements. And further to this, this grade fulfills all the major drinking water approvals. We have a range of grades for the food and water contact market based on Zytron, PPS, 40As, and Ecopax, and Stanil mainly for food contact applications, and Ecopax as well for food contact applications. The third example which I would like to talk about is from the industrial segment. So it is about unreinforced materials. So unreinforced materials, normally when we say metal replacement, you think about highly reinforced materials or glass reinforced or carbon fiber reinforced grades. But metal replacement can also be very subtle. So looking at applications in extrusion, like tubes or hoses, or injection molding parts like fasteners or cable ties, gears, applications in oil and gas industry like guide rods. So these are the areas where unreinforced materials could as well replace metals, and there could be requirements like high chemical resistance, stiffness, and strength at high temperatures. And just try to compare here modulus versus temperature for our Stanil and 40As, both unreinforced grades. And if you are looking for high stiffness and strength at temperature range 100 to 150, then 40As would be a candidate. Otherwise, Stanil also performs very good at high temperatures, and it outperforms PA66. Again, a range of grades that we can offer. To quickly summarize, in case you need hydrolytic stability, then look for PPS. If you're looking for mechanics at high temperatures, then 40As would be a candidate. Good flowability, thin walls, unfavorable position of weld lines or fatigue properties, fatigue resistance, Stanil would be a candidate to look at. And then high precision parts would be arnide PET-based materials. To look at the competencies that DSM can offer, so we have a very strong team of R&D people who can help us design and develop right materials. A very strong support in computer-aided engineering, which can help predict part failures and also help in design and simulation. A very strong application know-how, and of course in-house prototyping services that DSM can offer. To quickly summarize, we are active in several market segments besides automotive. The material choice depends on balancing application environment, long-term performance, and cost. And DSM has an extensive portfolio which opens up further opportunities for metal replacement. And we have a very strong track record in metal replacement, and we can build on our broad application knowledge to support our customers with tailored materials. So if you need more information, you can always visit our homepage or also plasticfinder.com, where you will find a lot of information about products, technical data, and application information. With this, I come to the end of my presentation. I thank you a lot for your attention. Thanks a lot.
Thanks, Jinish. Well, as discussed, we're opening up for questions now. So as a reminder, please submit your questions via the panel on the right-hand side of your screen. First question here. At the beginning, you discussed outsert molding. Could you explain or define this concept a little bit more?
Yeah, so outsert molding is like you might have kind of a metal frame, and so insert molding is for I'll start with an insert molding. So insert molding could be that there is a metal insert or a threaded insert, and then you are molding the metal or you are molding the plastic around it. So that is insert molding. When you talk about outsert molding, then it could be kind of a big frame. You can imagine a frame of a mobile, and then there are areas where you could mold some plastic. So here mainly the metal is the main part, and then you have some areas where the plastics could be molded. So that is kind of outsert molding. Yeah.
Okay, thanks. Another question here, is there any scientific way of validating plastic replacement with metal parts?
Plastic replacement with metal parts or metal replace? Yeah, I mean, I don't know if you mean metal replacement with plastic parts. I'm not so sure what is the question here, but I assume it is metal replacement with plastic parts. And yeah, I mean, there are methods of molding, scientific molding methods, but I'm not really sure. So I take this question and maybe I can come back.
Yeah, okay. Do you have any success case to share replacing metal?
Well, I already showed a couple of cases in my presentation today where we could replace metal with plastics, and there are several more that we can talk about. So if there is any specific area where you are looking at, then of course you can reach out to us, and then we will take it specifically for that particular application or case.
Yeah, okay. Another question here. You had a slide showing Weldline strength of a fiber reinforced material at greater than 100%. How is that possible?
Well, line strength, I'll just go to that slide. Yes. Yeah, so it's not it's not the percentage here, yeah. So it is not the percentage on the scale, but it is the strength here in terms of megapascals. So excuse me that is missing over here. Yeah. So hope that is clear now.
Okay. Another question here. You talked about different materials and applications. What about metal replacements with more known materials like PA6 and PA66, glass or carbon fiber reinforced?
Yeah, I mean, in case of PA6 or PA66, we have already several examples, so I did not talk about them today. But with our ultraflow grades based on Aculon ultraflow grades, which could be 50 or 60% glass fiber reinforced, we have achieved several metal replacement applications in consumer good applications, or also other structural parts. And also we have grades based on carbon fiber reinforced based on PA6 and 66 in our portfolio.
Excellent. Next question. What materials do you recommend to replace metal tubes or profiles?
Yeah, I mean, like I explained in the section about unreinforced plastics that we can offer, we have a range of grades for extrusion applications. So of course you can go with the PA6 or PA66 based grades for extrusion applications, but when you are looking for where the requirements are higher, like high chemical resistance or high temperature resistance or stiffness at high temperatures, then you could also consider grades based on our 40As unreinforced. And there are solutions based on PPS which are suitable for extrusion applications that we can offer. And also for profiles or tubes, it could be Ecopax, which is our PA410, which we could offer for such type of applications.
Okay, thanks a lot. Next question here. Yeah, this talks about a specific application. What is the best choice for pump water impellers?
Yeah, I mean, if you are looking at impellers, these are the parts which are in contact with water and also have to be very dimensionally stable. So here you would choose a material which is in hydrolysis performance, it's very good. So I would go for a PPS based solution in case of impellers.
Yeah, and if the asker wants more information, obviously you can reach out after this webinar. That's all for now, I guess. I don't see any other questions coming in. So also looking at the time, I think let's conclude this webinar now. And thanks a lot, Jinish, for your presentation and all the answers you gave. Well, hope to meet you in a webinar soon.
Yeah,
Thank you
thanks a
very
lot.
much.
Yeah.
Bye-bye.
Bye-bye.